yeah, welcome to the afternoon session where we have David's last lecture of this series.
Thank you. So, let me remind you what happened last time. So, we are proving that if we have a metric space B, finite Hausdorff measure, positive lower density, and its tangent, and Gromov-Hausdorff tangents are somehow flat, or maybe they are by Lipschitz images of our n, then E is rectifiable. And at the end of the last lecture, I kind of reduced, using measure theory, we reduced to supposing that E is alpha regular. So measurable is goes after the end. And then we have a good set of points in E where the tangents are nice. Right, so it has big measure. Nice tangents. And by nice tangents, I mean that for every point in G and every radius less than 1, E intersect BXR is close to a tangent. And this means that if we have I'm doing this just in the plane, if we have the square over here of radius r, then I can map the lattice. And I will pick how fine this lattice is later on in the proof. Okay, but for now we just work with a dyadic lattice. I can map this by Lipschitzly with some by Lipschitz constant sigma into the metric space. These are all points in E. Right. And we want to construct a Holder surface, or at least we want to iterate this so that we can construct a Holder mapping into the metric space. Right. So the basic idea is from now on, I'll only draw the domain, okay, just for simplicity. But what you have to imagine is I'm going to start filling in dyadic points. But points that I fill in mean that I can extend the map into the metric space. But there's no point in me drawing the dots over here too, because it just gets very complicated over there. So I'll just draw the dots in the domain. Right. So we know that these points are mapped into E. If the corners happen to be mapped into G, we can iterate, right? So if this guy here belongs to G, we can look at its tangent, right? So we look at a ball of half the radius. These points exist in the metric space, so we can find them in the tangent, and then we can use the tangent to fill in these other points, right? And this will allow us to fill in the points over here, right? And because of how all the estimates work, so these distances are like 2 to the minus. This is 2 to the minus 1. Over here we get sigma times 2 to the minus 1. This distance, of course, is 2 to the minus 2. And over here, it will get mapped to sigma times 2 to the minus 1 squared. Right. But this is okay because this is okay for our Holder map. Right. So for the moment, I'm going to just go through the argument for good points. Right. I'll explain the difficulties in doing things for the good points, and then we'll move on to the bad points. But just to repeat, the idea is we keep on iterating, and hopefully this will make the Holder map, and hopefully it will make sense too. So the idea is the corners of a subsquare correspond to points in G. We continue. We identify them. These points in a tangent or in the tangent of x1. Let's say that this is this corner point. Let's say here this is x1. And it, right? Okay. Now, the order in which we do this is quite important. Right. So suppose that we do. Let's just say that we never encounter bad points, right? Just for the time being, and we keep on iterating this. And let's say we iterate this 100 times, right? So then that means that in the domain we have, you know, lots and lots of lattice points that we've been able to identify. Right, and for this picture, I'll just draw one row. But you should imagine that this is a lattice with 100 squared, many points in it. Now I want to start filling in the points here. Right, so okay, I fill in these points, and now I come to this square. In order to continue, I have to identify all of the points that I've already found, right? Because I want to keep extending the Holder map. Right, so I come here, let's say this point is good. I look at all the points that correspond to this. I identify them in this tangent, and I try to continue. But this involves finding this guy. Right? Now, when I placed this guy, I naturally have an error, right? Because we always have errors. So there will be an error in placing this guy. So then if I try to fill in this square, I'll have this error that somehow will be incorporated in my estimates. So that when I place these points, they will inherit this error. Right? So that means when I come here, I will have an error for these 2 points. That also includes this error. Right? And if I go all the way along here, I will have an accumulation of arbitrarily many errors, and this is of course bad. Right? So the error propagates every time. So, and it gets out of control. So what we have to do instead is the following. We first fill in all of the one skeleton. So if this point is good, I say I don't want to fill in the whole square. I just want to fill in the boundary. Right, so I can place this point by only considering these 2. Right, somehow, if I just want to fill in this face, this guy isn't really a problem. So I can fill this one in without worrying about what happened to this one. And I can fill this in by only worrying about these 2. Right. So I can fill all of these in by only considering the error of their parents. Right? So I can fill all of this in arbitrarily many times, and I only have the error that comes from the green generation. Right, and I get to the end, and I have an error, of course, but it's only one error, right? And I probably missed some out. Maybe I can fill that one in too. So I go to the one skeleton by just encountering one error. And now I can fill in the face. Right? I can fill in this center square. I need to look at the parents, but now the parents, I don't need to worry about this square to fill in this one. Right? I can fill in this guy by only looking at the boundary points. Right? And so now I can go all the way like this. And I get an error, but it only depends on the dimension of it only depends on n, right? In this case, it's 2. Right. So I guess that's all I really have to say about this, without going into more details. But just somehow the way how we try to construct this whole map is important. We can't just do the first thing of trying to just fill in the whole square, 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 because I'll get to the end and the error will be massive. But if we do it in the right order, that doesn't happen. Right? So let me just say we have to be careful. We have to be careful. The whole map. Well, so that it's actually older. Do not explode. As we can about this. Okay, so maybe I can just say the same thing again, but with something a bit more precise. So when we place this blue guy, we get an error of the order sigma times 2 to the minus 1. So when I try to fill in this square, if I want to, I've confused myself now. If I was to then try to fill in this entire square, I would take this error of 2 to the minus 1 and it would be incorporated here. Right, so I get an error that would look like sigma times 2 to the minus 1 squared. And then here it will be sigma, well I should do this up here now. If I did it this way, here I have an error that's like sigma times 2 to the minus 1. If I fill it in this naive way, I get this error and it will be multiplied by the new error that I get. So it will be sigma times 2 to the minus 1 squared. Yeah, I get sigma times 2 to the minus 1 cubed. All the way down to sigma times 2 to the minus 1 to the n. And n is arbitrary, right, because it's the dimension of this lattice. Whereas in this case, I get an error that's sigma times 2 to the minus 1 to fill in this point. And now when I move to this next midpoint, I don't look at this blue point, I just look at the green guys. So again, I get sigma times 2 to the minus 1. Again here, I get an error of sigma times 2 to the minus 1. Right. And that's just, I can go all the way, and I only have errors of sigma times 2 to the minus 1. In general, when we want to fill in the ith generation of dyadic points, we will get an error. Well, not is how much the map expands the distance between the points, right? So it's really the whole so in general, we get a map that expands the dyadic points, dyadic lattice. So it maps, if we have 2 points that start off of distance 2 to the minus I in the lattice, they are mapped to, at most, sigma times 2 to the minus 1 to I.
How large can be sigma?
It can be as big as, I mean, it can be, it's a combination of the K that's in the hypothesis. And then there'll be another error depending on how good you want your tangents to be. So it could be just slightly bigger than K, but it's basically K, which of course, even if you don't care about Lipschitz tangents, but just norms, so it can be like square root of n. So it's pretty big.
But then say that it's controlled.
Yep.
If you take I large enough so that the sigma times 2 to the minus I is less than 1, then there's not a problem, right? Big power. And so if I is large enough so that sigma times 2 to the minus I is less than 1, then taking power.
Yeah, this here is a 1. This isn't.
Sorry.
Yeah. Yeah, thank you.
Then I see.
Yeah. Yeah. But if you do it the right way, you get an error like this. Yes, okay. Another point here is that the Holder exponent of this map will be such that this is 2 to the minus I times alpha. I think this is correct. Yes, okay. This number is bigger than 1, so I can take a say that this is correct. Sorry, something looks wrong here. Yes, it's without the minus. Maybe I should discuss this later. We'll talk about this later. You see, even if what Andrea was saying, even if this thing is, we can pick this to be less than 1 by choosing a final lattice, which is what we'll do at the end. So we could actually place 2 to the minus 1 by 100 to the minus 1, and then it would indeed get smaller. I mean, it would be less than 1, but we have to compare it to 2 to the minus 1 to the alpha. So it's not just that it goes to 0, it has to be bounded by whatever we pick it smaller than. Okay, yeah, so we'll fix that later. Okay. Right. So this is what we do for good points. Right? Now what do we do for bad points? So remember, what is a bad point? A bad point is if I have a corner, so it gets mapped somewhere, but it doesn't get mapped into G. Right? So a bad point is one where we can't continue iterating. Now, we can actually be slightly more flexible than that. It doesn't matter if we don't map exactly into G, because of course, down here I have an error of the size of sigma times 2 to the minus 1. So I can actually move the point by something of this order, and the errors will still be the same, right? I will just get 2 times this instead of 1 times this. So bad points are actually ones that, so these will be points that are mapped far from G. Right? And the farness can depend on, is exactly this distance. Right? So i.e. points P such that when I look at f of P, if I take a ball around this of size sigma times 2 to the minus 1 to the power of I, this is disjoint from G. Yes. Because again, all that will happen is that I get a constant in the estimates. So I can, if this is where my point P was meant to be mapped to, I don't mind moving around a little bit. And I can incorporate the errors. How far I can look around is exactly this quantity, because it's how much the map was already expanding the points in the domain. Right. And now we continue forever following this process. If we, at such points we just stop. We don't care about them for the moment. At such points we stop. And now we repeat forever. Right. So now just continue forever.
By stopping, what do you mean?
So by stopping means I completely kill this dyadic square. So I just completely forget about it now. So I stop here and I carry on everywhere else. And if I again encounter bad points, I just stop. So what this obtains is the following.
You just define a map on some sublattice.
Yeah.
So some subset of this lattice.
Exactly. So this gives a decomposition of the unit square as a set C, which is where we continue forever, and a bunch of cubes, a bunch of squares where we stop. Okay. So just to be a bit more explicit, I'll draw what the domain will look like after this. Right. So maybe on the first go we don't stop anywhere and we identify everybody. On the next go, maybe this square stops. This goes on. Maybe here we stop here. Here we go on, and then again we're repeating here. Maybe we can continue everywhere. On this one we stop. Here we carry on. Stop. Carry on. Carry on. Carry on. Carry on. Carry on. Stop. Carry on.
So if you stop, this means that you stop at the center of this.
Yeah. So it means that the kind of the parent dyadic points are defined, but then I don't continue on the inside or even anywhere on the boundary.
Anywhere.
Yeah.
So just one point, it's just one. But if just one point dies, then you would also.
Yeah, it doesn't really matter. You can do either one, and
Okay.
yeah, because if this guy is bad, then there's only control of many neighbors, so it doesn't really matter in the estimate whether you continue or not.
The map is simply not defined in the direction square or differently constant?
So I guess the map will be defined on C, because that's where we continue forever. So that's the complement of the shaded squares.
Yeah.
I have a holder map on this, so I can always extend to the closure anyway, which will fix any of the boundary points. Right. So this is a stopped square. And on C, we get a holder map. Right, we get a holder map. F that goes from C into E. Now there is, maybe I won't discuss this because it's more details, but I won't write it down, but I'll just say it because Andrea brought it up. At this point, to actually get that this map is Holder, you have to pick two to be very big here, right? Because we need to pick alpha so that this quantity is at most 2 to the minus 1 to the power of alpha. And this is only possible if this thing is less than 1. Right. But this is okay because sigma is fixed at the very start. Right. Sigma is fixed. We then pick our lattice to be very dense so that this quantity is less than 1, where 2 is the subdivision of the lattice. Right. But I won't write more details about that because I think there's already quite a lot of details. But again, we can do that by just picking our tangents to be better.
What you want to say so that you are heard that you have to yourself? Don't you need to know that you have not many spheres excluded because so you control it only on small scale, and then if you want to talk, don't you know?
Yeah, we only want the one bound. We only want the upper bound for the Holder.
It's not by Holder.
No, yeah, it won't be by Holder. It's just Holder.
Okay.
Right. And we have the property that so on the stop squares. So if we stop. Or I mean, if Q is a stop square, right, with the length of Q is 2 to the minus I, then we know that there exists a ball of radius sigma times 2 to the minus I, sigma times 2 to the minus 1 to the I. That's contained in the complement of G. Right? Remember, it's contained in the complement of G. And now the point is that the Holder exponent is such that if we look at 2 to the minus I times alpha, this is exactly this quantity. Maybe this is right, and this is the radius of the ball. And the fact that we can do this is crucial. That's probably not very visible. Okay. So now, for the final part of the argument, we need a surface. Right. So this Holder mapping is only defined on this, positive measure set. So there's no reason why it's a surface. So we need to extend it so that we get a surface. Now, of course, in X we may not have any surfaces, right? Because X or E may be a positive measure Cantor set. So we can't extend into X, but what we can do is put everything inside L infinity and we can extend there, right? Or in other words, we enlarge the metric space in order to construct a surface. Right. So we need, for what will come, we need a surface.
When do we know that the measure is positive? It may happen that the first cube is bad.
Yeah, you're right, it won't happen because we'll estimate it in a bit. Okay. But yeah, you're right. You can at least make sure that the first few sets, the first iterations are never bad by picking epsilon small, wherever epsilon was. And that's what will happen at the end. So we need a surface. So we want to extend f to the whole of the square in order to get a surface. But x may not have, for topological reasons, x may just simply not have any surface. Right? It's impossible into x for topological reasons. But if we consider D as a subset of L infinity, then of course there are no topological problems. And one can always extend Holder maps into L infinity. This is actually just a special case of the McShane extension theorem. Right, so McShane extension allows you to extend Lipschitz maps into R. Each of the coordinates here are real value, they are real value coordinates, so you can extend coordinate by coordinate. And a Holder map is just a Lipschitz map with respect to a different metric. Right? So just by using McShane, you can extend the map that we want. So by McShane, we get f that goes from 0, 1 into L infinity. Holder. So now we get our surface, and our surface is just going to be the image of this thing inside L infinity. S is f of 0, 1 is our surface. So we extend, or we somehow, we don't really construct the metric space because just McShane extends it for us. But we somehow build this slightly bigger metric space so that we get this surface. Of course, we need to check how much extra space we need to do this. If we add lots of extra space to construct this surface, it's going to be useless. Right. The important point is that we need to estimate how much larger S is than E.
Can you remind me of what we are doing? So we would like to prove that rectifiability. So we want to see that in the surface there is a rectifiable subset.
Yes, we will use the topology to prove that there's a rectifiable subset. But we need the topology in order to do that. And if we obtain the topology by just adding tons of stuff, it's going to be useless, right? So we need to make sure we don't add too much. So now we need to estimate how much more stuff we add. F is a Holder map, so we surely can't estimate how much measure we add because Holder maps will add infinite measure. But we can estimate content. So we cannot hope to estimate the Hausdorff measure that we had. Right, simply because f is polar. It could extend it and be a snowflake. Right, but we can estimate Hausdorff content. Right, and so we can just do that now because it's straightforward. So if we want to take the content of f or of the extension, so this is just simply the square without c, right? Because we've already defined c. This is just a union of squares, so we just estimate everything square by square. This is at most the sum over the stop squares of the diameter of f of q to the n. This is comparable f is Holder. So the diameter of the image is like the diameter of the domain to the power. So this is at most the length of q to the power of n to the power of alpha. Right. And now we use this. So this is the length of q to the power of alpha. Right. So the length of q to the power of alpha is the radius of the stop ball. So this is the sum of the radius of bq to the power of n. Right. Now we use the fact that the measure is alpha's regular. So alpha's regularity. Oh, and of course, we can construct it so that the balls are disjoint. That's not too difficult. But now we use alpha's regularity. This is at most the measure. So all of these balls live in the complement of G. Right, and they're all disjointed. So this is at most E without G.
Times the constant.
Oh yeah, times the constant. And this is at most epsilon. So this is why we don't stop at the start. So just to summarize that, by adding a tiny amount of measure, we can construct a surface. So, are there any questions?
So I don't see immediately why the balls can be chosen disjoint.
So I think at this step you can just use something like the 5R covering lemma, and then you will just get an error up there of a factor of 5, and I think in this case you can just use the 5R covering lemma and you get them to be disjoint. Okay, so now we've got a surface. Now what we want to do is construct a map back to the unit square. Right, so we now construct a map. A Lipschitz map G from our surface back to the square. How we do it is the following. So we have our initial lattice, right, which is the one that we get from the unit scale tangent, and we simply map. So we just invert the surface map back on that initial lattice, right? So for points P in the initial lattice, so this is the green one. I think it was green, maybe it was blue on this picture. But the initial lattice, right? We define G of f of P to just be P, right? So these guys get mapped into the surface somewhere, and G just inverts this on these points. And now we can extend G to a Lipschitz map on the whole of the surface. Right. Again, just by using the chain. Right. We extend G to a root n Lipschitz map that goes from the surface back to the square. Now, so this is a root n Lipschitz map, and it fixes the initial lattice. So if we pick the initial lattice to be really, really fine, we can, by using topology, we can make sure that the middle half of the square is always covered. So maybe I'll draw something slightly more convincing for that. So if we choose the initial lattice very fine, we will always have that G of f of the square contains, let's say, what's the half square? I guess it's 1/2. Well, let's say 1/4, 3/4. Right. Where very fine only depends on the square root of n. Right? Because if I pick this lattice to be really, really fine, what's the worst that can happen? I have a square. I can try and stretch this as much as I like, but I'm only square root of n Lipschitz, right? So I kind of like, I can only bend it in slightly around the edges like this. And I will never be able to not cover the middle of the square.
Oh, but shouldn't this be invariant on the scaling? I mean, if you scale everything domain and target, right, I mean, the situation doesn't change, right? So I don't understand this properly. But the finement, I mean, the sort of sufficiently fine, what is actually gives you.
Yeah, so sufficiently fine just means how good my tangents are. Right.
So you look at it in the terms of approximation of the tangent,
Yes.
and then you get a better control.
Exactly. Yeah.
Okay.
Right. So this means that, so let's just say, so we choose it so that G of S always contains the middle 1/2 square. Right. And so in particular, the measure is always at least something like 1/4. Right. And now the point is, because we only added, okay. What I want to say is that G of our metric space is big. Right? But remember, we had to add stuff here to construct this surface. And now we use the fact that we didn't have to add very much in order to estimate the image of E. Yeah. Right. So G of, so if we want to estimate the measure of G of E, this is G of S minus the extension. Right. The measure of G of the extension. Let me write this out, just to set it out a bit more. So, G of E is at least as big as G of F of C. Right? So, C is where we didn't stop, and C always maps into G. Right? So, in particular, it's always in E. Right? So, we didn't stop on G, on C. And C goes into right. So now this is just simply the measure of G of the surface minus the complement of the C. Sorry, G of F of this. Right. Now we have a bound on this, right? But we only have a bound on the content of what we add. But G maps back to Rn. So, and on Rn, content is just Hausdorff measure. Right? So on Rn, G maps into Rn. And on Rn, measure is equal to content. So this estimate is at least, right, so G of S is at least 1/4 of n minus, and here, right, so I have G, which is a square root of n Lipschitz map, times the content of this, which I estimated up there is epsilon. Okay, we're nearly done. So so we have this, we've constructed this map G that has big image. Well, what properties of G do we actually need to prove this? So obviously here we have a square root of n, so we depend on the Lipschitz constant. And we need this argument that says that the image of the surface is big. And so to do that, we use the fact that G is the identity on P, on the points P in the initial lattice. For this topological argument here, we could actually wiggle these lattice points ever so slightly, and we would still get the big image property. Right. So we only require two properties of G. One is that it's square root of n Lipschitz, and two is that it maps the initial lattice. very close to the identity. Right? So, what that means is that we have an open subset of the square root of n-Lipschitz maps. Right, so i.e., we have found we have an open of root n x, well, let's say e, to Rn that maps E onto a big state. Right? And so now you have to remember back 2 lectures. If E is purely unrectifiable, this is impossible. Right? By the nonlinear projection theorem. Right? So if E is purely unrectifiable, this is impossible. If E is not purely unrectifiable, but it's simply just not rectifiable, you take the purely unrectifiable piece and you run this argument for the purely unrectifiable piece. So, in general, if E is not rectifiable, this argument, run the argument on a non-trivial purely unrectifiable case, and we get a contradiction. So E has to be rectifiable, and that's the end of the proof. Okay, so yeah, that's the end of my lecture. So.